Welcome back. This is part 3 of my video set for implicit differentiation. Again, these examples came from the textbook Calculus Early Transcendentals, 4th edition, by Larson, Hostetler, and Edwards. We've been looking through these 4 examples. We're on number 3 right now. The graph of this implicit function is actually the graph of an ellipse that has been rotated. I think, oh yes, yeah, I've got the graph here, kind of a rough graph. So it's not our usual ellipse that we think of, but it has been rotated, and we're going to try to analyze this function according to where it increases and decreases, and we're going to focus on this ordered pair that satisfies the equation. The ordered pair is square root 3 comma 1, and we'll determine the slope of the curve in that neighborhood. Okay, so before we approach the entire problem, I thought we might break down the problem into smaller pieces. Let me move these papers. Okay. So as we move through the problem, we're going to be differentiating. We're going to be differentiating with respect to x. And the first term we're going to come into contact with is 7x squared. So that just needs the power rule. And that derivative would be 14x. Later in the function, we'll come across the term 13y squared. And we notice that the variables are different. We're assuming y is a differentiable function of x, and we're going to take the derivative with respect to x. So not only do we need the power rule, but we need the chain rule, and we'll have to multiply by y prime in the end. We'll come across a constant. Its derivative is 0. And then here's a different kind of term than the previous 2 examples. We're going to come across a product, x times y. And so we will need the product rule because we're assuming y is a differentiable function of x. Okay, so the derivative of a product is a sum. We take the derivative of the first factor, leave the second factor alone, and add to that the second factor times the derivative of the first. I said that wrong, but I've written it correctly, I hope. Let's check. The derivative of x times y plus x times the derivative of y. Yeah. And more specifically, in the problem we're going to look at, we're going to have the derivative of this multiple of x times y. No problem. We can associate 6 square root of 3 with x. And when we use the product rule, we'll take the derivative of the first factor, which will just be 6 square root 3, leave y alone. Then we'll leave the first factor alone and just take the derivative of y. So do you see how that differs from the derivative above it? The derivative of the last example is just 6 square root 3 times the derivative of the previous example. Oh, excuse me for hitting my microphone. Make sure that's in the right place. Okay, so I need to find the list of the derivatives we're taking. Get that back where you can see that. Looking at example 3 now. And we're going to want to find the equation of the line tangent to curve 3 at the ordered pair square root 3 comma 1. Remember, that was the highlighted point on the ellipse. We're going to take the derivative of the left-hand side, 7x squared minus 6 square root 3 x times y plus 13y squared minus 16. And we'll take the derivative with respect to x of the right-hand side. Okay, we've moved through these derivatives, so let's move again. The derivative of the first term, 14x. The derivative of the second term, that's going to be a sum. That's going to be negative 6 square root 3 times y plus negative 6 square root 3 x times y prime. Okay. We'll double check that in a minute. But as we continue on, we use the power rule to get 26 y times y prime. We won't forget the derivative of the constant, which will be 0. And then on the other side, the derivative of 0, just 0. Okay. Maybe we can take a quick moment to compare what we've written there with the derivatives we had earlier, if I can find them. I'm going to move that first sheet. Okay. So we had the derivative of this product with the positive coefficient, and we got this sum. The only difference is I associated down here in the green the negative with 6 square root 3. So when we took the derivative of this, we'll call it a negative product, we ended up with negative signs or subtractions. Okay. Now if a person just wanted to find an expression for y prime in terms of x, y, and y prime, then the next step is to treat this like a linear function and solve for y prime. Isolate y prime. Now we saw in the second video that we could make the algebra easier. We could do the substitution right now, and everywhere we see an x we could substitute square root 3. And everywhere there was a y, here and here, we'd substitute 1. Then the only variables remaining would be these y primes. We saw that in video 2. But let's proceed as if we were required to get y prime by itself so that we can practice the algebra. Okay. So we have 4 terms on the left-hand side of the equal sign. 2 of them contain y prime. The other 2 do not. Let's move these first 2 terms to the right-hand side of this equation. Okay, I hope we'll have room here. So this third term remains. The fourth term remains. And we'll subtract 14x from both sides, and we will add 6 radical 3 times y to both sides. On the left-hand side, both terms have a factor of y prime. So we can factor out that common factor. It may not be the greatest common factor, but it's a common factor. And that leaves us with the sum, negative 6 square root 3x plus 26y, in the parentheses. We'll copy down the right-hand side because we want to keep the equation balanced. Okay. So this equation that describes the relationship among x, y, and y prime is the same as either of the 2 previous equations. Okay, well now the algebra is almost done. We can divide both sides by this sum. Y prime is by itself, and we have negative 14x plus 6 square root 3y all over negative 6 square root 3x plus 26y. And that gives us y prime in terms of x and y. Since we wanted to focus on the ordered pair square root 3, 1, in our expression y prime, in both places we have an x, we'll substitute radical 3. And in both places we have a y, we will substitute 1. So we get negative 14 times the square root of 3 plus 6 square root of 3 times 1 all over negative 6 square root 3 times square root 3 plus 26 times 1. And you may have thought along the way, hey, down there in the bottom, those radicals will simplify. So yes, we'll do that. Along the top, we have like terms, so we'll add their coefficients and keep the radical 3. And in the denominator, radical 3 times itself is just 3, and 3 times negative 6, well, negative 18. And it's not a very pretty number. Yeah, what do we mean by pretty, right? But simplified, we get the ratio negative 8 over square root 3. Say that again, negative 8 times the square root of 3 over 8. Double check. And that will simplify to an irrational number, negative square root 3. Okay. So if y prime is negative, that tells me that the function should be decreasing near that ordered pair, or at that ordered pair. And if we return to my not very good picture, but something I drew myself, it's not unreasonable to think that the curve might have a slope that's close to negative 1. This would be a little bit more than negative 1 in absolute value. Okay. Now this line that I drew that is supposed to best approximate this curve near square root 3, 1 has an equation. We know the slope of that line would be negative radical 3. And then we need to add in x1 and y1. So that ends it for example 3. Let's see what we might turn to in example 4. So preview for part 4, just to see if you're interested. We're going to return to example 4 here, which has a really interesting graph. Thank you for your attention.